Hello, this is my final project. It's sudoku.lisp. Solves sudokus. My overall motivation for this project was a professor that said that there should be a sudoku competition at DePaul. He said he really likes sudoku, so I thought that was interesting, and I thought it would be a good application of symbolic programming. The overall goal of this project was to create a program that, well, solves sudokus. And it solves all the daily Sudoku stuff, which I'll show later. My code over here, I represent the Sudoku board as an association list where the cars of every element would be the so-called indices. These would be where the number that of each square is where it is on the board, and then the cutter would be the possible candidates for that specific square. And the whole point of it is to reduce everything such that it will only have one thing in its cutter, meaning that we've solved this. We use constraint propagation. So over here, I just have some variables like empty board and board, which I set initially to be empty board. I have some examples, puzzles. I have a print function, which I can show later. These are some functions that can reset a board or place a point where I need it. And I also have some referencing functions, mostly used by the computer, used by the solver, to figure out what will be the things that I eliminate things from, which is seen here in this neighbors function. This will tell me all the neighbors of a certain number. So if I were to say neighbor 0, that would tell me everything that's in the 0th row, the top row, or in that column, or in that first top left box, because 0 would be the top left. I also have a step where I loop through and I look at all my fixed points and eliminate the lone candidates of every fixed point from all of their neighbors, so that it will be easier to solve this problem. It's technically not necessary, but it makes things nice. I have some functions that check if the board is legal, and even if it's done. And my last step is a brute force algorithm that basically tells me, hey, check every possible candidate of every cell, and it goes recursively, so it'll start on the first cell, on the 0th cell, and it will look at all the candidates and loop through, and it will recurse on that candidate and keep on going through the entire list. If we get to the point where our cell is 81 or greater, then we know that we've solved the puzzle. And if it fails, it will backtrack, and here's the backtracking step. Probably the hardest thing of this project was coming up with a representation that works. What I mean is up here, how I would have all the candidates represented within that association list. I went through multiple different crises on whether I should use row and column or use numbers, but I realized that given the structure of this problem, it wouldn't matter. Another difficult thing was deciding if I should do things functionally or not. I tried using my reduction step. I tried to do everything functionally, but I found that it just ran slower. So side effects were kind of necessary to make this run better. And also this brute force step, it came as a moment of inspiration, but up until then, I had a lot of trouble. The premise of it is not so difficult, but getting it to work on my specific representation of this project is different. It's different for every representation, so that would be why that was difficult. And now here's a example. So we say load sudoku.lisp. If I want to build a puzzle, let's say we build the very hard puzzle. Very build puzzle. It's going to be very hard. This was a puzzle seen on. This is a puzzle I found online, and it was under the very hard category. But if I just hit solve, it ran a little bit slower, probably because of the recording software. Normally it does it instantly. But you can see that I do the reduction step on this puzzle, and it doesn't solve it. But I get a few things. I get this 3. I get this 2, which is pretty nice. And then the brute force step just kind of fixes everything at the very end. And I can also reset the board. And I could do something like, we could do very easy. And if we solve that, you'll find that I only needed the reduction step. I didn't have to use the brute force at all, which is quite nice. After doing this project, I found probably the most important thing I learned was that the representation of how to do things is just so important. But I enjoyed the one that I used. I could have used an array, but it's harder to use mapping functions on arrays, which I used mapping and remove, if not quite a lot, in these auxiliary functions, which I also should have written with the macro. That's one major thing that I regret, but it works. I use lambda functions in nearly every function that I had, because having something there that was just on hand is quite nice. And yeah, there are also some puzzles that don't really build, reset, board. There are some puzzles that are extraordinarily difficult. Here's one that has only 17 clues. If I try to run this, if I try to solve it, it actually doesn't work, which is quite disappointing. So I probably shouldn't hit solve. Perhaps if I had a stronger computer. But I found that one online, and it was only 17. It only has 17 hints, which is astonishingly few. That's the lowest that we've found we can solve. At least that's what mathematicians say. I don't know the proof on that, but yeah, that's my final project.